Hello, welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to ESO Paranal Observatory. So, well, just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory since 2010, and I am also part of the staff of the Astronomy Center in Antofagasta. And regarding my personal hobbies, well, I am very interested in telescope observations and astrophotography. Well, today is Hector Salas as the producer. So, hello, Hector. How are you?
Hello, Farid. I'm fine, and you? Okay,
Good.
so let me to introduce myself. I'm a PhD student at the Leibniz Institute for Astrophysics in Germany. I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds galaxies. And I've been a member of the team of guides from Paranal Observatory since 2019, when I was doing my master's in Antofagasta. Since I'm the producer today, I will be taking a look at all the questions and comments that the viewers post in YouTube or Facebook, and I will try to come up with answers. Okay, so you can start to do for it.
Okay. Thank you, Hector, for uh, for your greetings. So, well, ESO wants to be with you during these virtual visits, and of course, bring astronomy directly to your home or wherever you are. So please remember, you can send your questions and comments during all this streaming. So I can imagine you already have some questions. So please don't forget to leave your questions or comments in the comment section of this streaming on Facebook or YouTube. So you can say also your name and your city. So later we can announce it during this tour. So Hector will be waiting for all your questions. Okay. And also, please don't forget to share this experience in case you like it with the share buttons on Facebook or YouTube. So, okay, now we are going to start with this tour, and we want to help you to understand the place of our visit. So, we will begin with some information about the European Southern Observatory, or ESO. So, ESO is composed of 16 member states. So, in a few moments, we are going to see, okay, this picture. So you can see that the headquarters of ESO are located in Germany, and also Australia has recently joined ESO as a strategic partner. Chile is the host state and home of all ESO observatories. So from the 1960s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observations, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories, such as ESO, to our country. As a result, Chile offered its territory, and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. Why? Well, to enable important scientific discoveries and incentivize the promotion of and cooperation in the astronomy field. So right now you will see a picture with the three observation sites of ESO in Chile. So here we have the Chajnantor Plateau, the site of the ALMA and APEX radio telescopes. ESO is part of these places for radio astronomy alongside other international partners. Additionally, south of Atacama Desert at 2,400 meters, we have La Silla Observatory in the Coquimbo region in Chile. So this is observatory is the home of several telescopes, such as the NTT or the 3.6 meter ESO telescope. And this one is using the HARPS instrument. And this is an exoplanet hunter. So finally, we have the place of our visit. We have the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT, the most advanced visible light telescope on the planet. And in a few more years, we will also have the Extremely Large Telescope, um, or ELT, that, that will be the biggest visible light telescope on Earth. And also, the CTA will be an array of telescopes focused on capturing gamma rays. Okay, so now we have a better picture. So now let's travel to the Paranal Observatory. So now virtually you are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago. Specifically, about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. So this mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And what is the ocean? Well, the Pacific Ocean is located below of the cloud cover you can see in this animation. But why those clouds if right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt current. This is a cold current near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above sea level, and keeping below the cold, humid, and basically bad air for astronomy. And about the layer, instead, we have the hot, dry, and less dense air. So this is something like the good air for astronomy. So the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Well, we have a different natural barrier around this area. So about 200 kilometers to the east, we have the Cordillera de los Andes with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So, overall, this is one of the best places on Earth for astronomical observations. Okay, so right now we will change the view to have an even closer look to Paranal. So, as you can see, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. So, do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. This observatory is a true oasis, so you will see how in one of the driest deserts we have a lot of life, and of course we have a lot of science. Okay, so right now we will visit the summit of Paranal. So we are going to change the view. Can you confirm, Hector, if it's visible?
Yeah, yeah, you can see it.
Okay, thank you. So, well, in front of us we have the Very Large Telescope, or VLT, its acronym. So if you see the amount of buildings, four giant domes and other small and rounded ones, we are going to visit them as well. It is clear that the Very Large Telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. Here you can find the four unit telescopes, or UTs, each one with a primary mirror of 8.2 meters in diameter. So these are the giant ones in your screens. And the other small ones are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. So these are the auxiliary telescopes. We have one here, we have two, we have three, and we have four. Okay, so we have unit telescopes and auxiliary telescopes. Now, each UT has a name in Mapudungun. This is the language of the Mapuche culture, natives from central and south of Chile. So here we have Antu, which means sun. Okay, this one is Cuyen, which means moon. Okay, this one is Melipal, which means four stars, but is associated with the Southern Cross constellation. And here we have Jepun, which is associated with Venus. It's a concept referring to the evening star. So these closer ones, as I told you before, are the auxiliary telescopes. Okay, they are mobile and they can be moved using a rail system, as you can see here, up to 30 different positions. They were specifically designed to work all together as a single big telescope with a variable diameter and able to reach up to 200 meters, as you will see in a few moments in a short video. Okay, we have the video here. So this technique is to combine light from several telescopes is called interferometry. So we are able to observe much more specific details if you compare this with the individual telescopes. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits and some information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. Okay, so right now we will come back to the tour screen. Okay, so now you will have the opportunity to visit a telescope. We are going to visit the UT3 Melipal. We can't enter to all the telescopes, but don't worry about that because the four ones are identical in size and shape. So the only difference are the instruments inside. You can know more about the instruments on the ESO website. Okay. Okay. So now we are going to enter the UT3 Melipal, and here we are. Now we are on the UT3. What can you see? Well, this is a giant telescope. Okay, as you can see, it's very big. So now we are on the last floor of the telescope, at the same height of the main mirror in front of us. The mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thick, created from a ceramic and flexible material called cerudur. So I am doing a close-up so you can take a better look at this mirror. Okay, so please remember the material is a ceramic and flexible material called cerudur. Okay, so now how can we point to this? How can we point the telescope to the sky without breaking it? Well, we are going to see this telescope from another angle in order to explain that. So we are going to change our perspective and take a look from here. Okay, so the mirror, as you can see, is mounted over this white structure. Okay, can you see it? This is a cell supporting all systems assisting the mirror, including something called active optics. So here you can see some little gray boxes here. They are called actuators. So they are some kind of piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of this concave mirror. Otherwise, it could suffer deformations just because of gravity. And those deformations, imperceptible in a first view, could be critical in the result of the observations. Okay, so how is this working together? We will come back to explain that. So we are going to change the position again to take a look to this telescope. Okay, so in order to explain this, we are going to display a short animation to understand how the light is going to the telescope. Okay, here we have the animation. So you can see that first we have to open the doors of the dome, okay, in order to let the light enter to the telescope. And the telescope will receive the light first in the primary mirror, 8.2 meters, and once the light enters, it is concentrated and reflected to the secondary mirror, then reflected again to a tertiary mirror, and the tertiary mirror will reflect the light to one of the available instruments. So we have three instruments in the telescope represented by those red, blue, and green squares or boxes. So they represent the instruments. So we have three available instruments to process the light. Okay, so that's why that's how the telescope is receiving light. And you need to understand that after all this process that is done, the instruments will convert this light into a digital signal, and the digital signal is transferred to another facility. So because the astronomers are not inside this place, they are working from some a place called a control building. So this control building is located in a different location, and we will also visit virtually this control building in a few moments. Okay, so but this is in order to understand how this telescope is working. Okay, so in this way we are finishing our visit to the telescope. So we will come back to the platform again. So I am going to change the view to move to the VLT platform, and here we are. So and from the platform we will change the position to the control room. And the control room, as I told you, is the workplace for astronomers and scientists for performing the observations. So here you can see that we have a building in a different level, not in the same level of the platform. And this is basically the control building. So we are going to take a initial look to the control building from the opposite side. So you can see that this is a big building, and inside we have the astronomers working at night. Okay, so we are going to enter there in a few moments, but before doing that, I don't know if we have some questions or something to respond so far. So Hector?
Okay, so we have a few greetings from Amsterdam, Swaygraven, from Scotland, PTONPC, and from Turkey, from Highlander. But we haven't had any question yet, so let me ask you a typical question that people ask in the tours. Do we need to do some sort of maintenance to the mirrors?
Yes, we have to do some maintenance to the mirrors. So basically, we have to clean the mirrors, and we have two ways to do that. So in order to explain that, I will come back to the telescope. So I can show you better that the mirror, in order to clean this surface, we have one option. Okay, this is the easy way involving carbon dioxide. A carbon dioxide snow is something like a foam. So basically, for this maintenance, you need only a few engineers, maybe one or two. So they need to rotate the mirror a little bit, and one of the engineers will spread this carbon dioxide snow on the mirror from a safe distance. So basically, this element will remove dust from the mirror because we are in the desert, so we have dust. So because the mirror is tilted, it's inclined, this carbon dioxide and the dust are going to fall to the ground by gravity. Okay, so this is basically the easy way. You need to do that about once a month. and that's enough to keep the mirror free of dust. And the other way is the complex way, and you need to do this maintenance about uh, every 18 months. So this is 1 year and a half. So in order to do this additional maintenance, you need to remove all this structure. I mean, you need to remove all the mirror, all of this, and also this white cell. Okay, so basically you need to extract all this structure from the telescope, and you need to transfer all the mirror using a special vehicle to the base camp of Paranal. So in that place, we are going to do a process called recoating. So a recoating is basically to remove the aluminum layer in the surface of the telescope, and we need to put a new layer of aluminum. So all this process takes about 3 or 4 days. During this time, the telescope is not working because we don't have any replacement. And after the mirror is ready, with the new aluminum layer, we need to bring the telescope again to the platform. We need to lift the telescope. I mean, we need to lift the mirror. We need to install the mirror in the telescope, and the telescope will be ready again for observations. And the mirrors will look like a new mirror. Okay, so that's why it's so important this additional maintenance, and that's why, as you can see in this picture, the mirror looks very nice, looks very clean, looks like a new mirror. But you need to consider that Paranal has more than 20 years of operations because it was inaugurated in 1998. So basically, that's how we clean the mirrors.
Okay, thank you for it. We have a question here about when we'll be able to find new life on other planets, and they mention specifically the Hubble, but uh, this could be any telescopes that could do it. And we don't know when, but we would like to ask you how we would find it. So the best way to do right now, from a telescope either in space like the James Webb or Hubble, or from Paranal or other observatory in Earth, would be to take a look at the atmosphere of an exoplanet and look for signatures of life. So, for instance, here in the Earth, the carbon dioxide is mainly produced from living creatures. They breathe oxygen, they produce carbon dioxide. Also, some things like methane, But some of these things could also be produced by, let's say, volcanoes or other geological phenomena. So the way to do it is rather to look for a single signature like oxygen. You look for a combination of different signatures. So oxygen, methane, and maybe carbon dioxide. I don't really remember which one was the ones that are more likely to be. But you will look for this combination of signatures, and that will be an indicator that there might be life there. So that would be one way to discover it.
Okay, Hector. Well, thank you. Um,
You're welcome.
yes. So I don't know. We can continue or want your questions.
Uh, let's go with one other of the typical questions that people ask. What happened with earthquakes? Because Chile is a very seismic country. Do we have any special measures in place in the observatory?
Well, yeah. We have some protections in the underground. In case of an earthquake. Well, basically, this is a very strong foundations. And in theory, just to give you an estimation, we can be okay even with an earthquake of 8 magnitude with epicenter in Antofagasta. So you can see that it's pretty strong. And so far, yeah, we have had some earthquakes, some tremors, but so far nothing too important to worry about. In case of an, I don't know, mid-level earthquake, some engineers can go to the telescope and just take a look to to be sure that everything's working fine. But most of the time, we have small tremors, and you can find a monitor in some rooms in Paranal, and this monitor usually says ignore. That so this is just a label to say, okay, this is a very small tremor, and there is nothing to worry about. So no, I think we have been doing a very good job in terms of the earthquakes.
Okay, thank you, Farid. Let's continue with the tour then.
Okay, thank you, Hector, and I hope we can still receive more questions from the people. So now we are going to continue, and the next stop, as I told you before, is the control room. So we are going to move to another location, and we are going to access the control room. The control room is located in this building, as I told you before. It is located at a different level if you compare with the telescope platform. So from this new perspective, we can see the building where the room is located. So now we are going to enter. So here we have the control room of Paranal. As you can see, we have several separated workstations. Okay, so each workstation is dedicated to a single telescope. So for example, in this case, this workstation is only working for the Melipal telescope, UT3. Here we have another workstation, but only for the UT4, Jepun. Okay, so all operations with Jepun, for example, are from here. If we keep working, basically in this virtual corridor, we are going to find the workstation for UT1 and 2. And if we cross to the other station, we have this station for Kuyen, UT2. Okay, so basically all the telescopes, instruments, and systems explained before are controlled from here. So during the day, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. Each night we have a telescope operator and an astronomer per telescope. So we are going to access this workstation to basically take a look at the people working here. So because we have usually a telescope operator and an astronomer, well, let's suppose that this person is the telescope operator and this person is the astronomer. So the telescope operator is in charge of the technical details and the movement of the telescope. So it's someone like the pilot of the machine. The ESO astronomer is in charge to direct the scientific observations and will decide the next step. So he's like the co-pilot. Okay, so the observations are performed by experts from ESO for scientists from all the planet. Okay, so this is what happens here at night. Okay, okay. So now that we know more information about what happens here at night, about the workplace for astronomers, we are going to move again to the platform because we will show you more information. But in this case, regarding some discoveries. So now you have a lot of information about the observatory in general and the people working here. So now, as I told you, I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean La Silla, Paranal, and Chakrantor. So scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, and also others located in the more distant places in our universe. Okay, so now we are going to explore a list of the top 10 discoveries from ESO sites so far. So please enjoy it.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history. Elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang Theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, well, this was the top 10. Very interesting, of course, but we have just one more thing. We have something like a bonus track. So let's take a look at this right now. This news is regarding that a team of astronomers was able to capture the first image of a black hole. The Event Horizon Telescope, or EHT, its acronym, is an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, and this was able to achieve the first direct evidence of a supermassive black hole. So this picture reveals the black hole in the center of Messier 87, a massive galaxy in a close galaxy cluster in the Virgo constellation. This object is located 55 million of light years from the Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so this is the picture of this black hole. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries thanks to the ESO telescopes and the scientific stuff behind them. So now we can continue. And from the platform again, we are going to do a very special activity thanks to this virtual tour. We are going to observe the night sky from Paranal. So here you can see we have night landscape. Okay, as you can see, the sky is almost completely dark with the last traces of light from the twilight. The moon is below the horizon and the sky is full of stars. So here we can see in all this beautiful sky a very popular constellation just above of the AN2 telescope is this one right here. This is Orion's constellation. In the mythology, this represents a hunter. So I am going to do a close-up of this constellation. So you can see this represents a hunter in the mythology. So you can recognize it with those three stars somewhat aligned, representing Orion's belt. And inside of Orion, we can see another interesting object. That's the Great Orion's Nebula. This object with a little bit pink tone. Okay, so this is a very popular constellation. It's very easy to recognize, very easy to see. And but now we are going to change the position and move to the brightest star of the night sky. We are going to move to this star here, and this one is called Sirius. So this star belongs to the Canis Major constellation, representing Orion's hunting dog. So a little bit down, next to and 2, I will change the position again. A little bit down here, we have another interesting object. We can see the Pleiades, this one. The Pleiades is an open star cluster located in the Taurus constellation. Okay, so this one. So the majority of those objects are visually close to a specific area, very populated with stars. So if you see, this area has a lot of stars, okay, if you compare with other areas of the sky. So actually, we are looking at one of the Milky Way arms when we see that this area full of stars. The Milky Way is our galaxy, and our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, another area full of stars between Scorpius and Sagittarius constellations. And you can see all this area from this hemisphere, the southern hemisphere. So now we are going to move to another sector in the sky to find two spots in the night sky. So we are going to change the direction, and you can see those spots. Okay, we are going to do a close up. So these spots right here are the Magellanic Clouds. Up here is the large Magellanic Cloud, and down there is the small Magellanic Cloud. Now, they are not actually clouds, of course. They are galaxies with an irregular shape, both visible to the naked eye in a clear night like this one. So this name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So during this time, the people were unaware about what a galaxy is. Okay. Well, another important area right here is the smallest constellation of the sky, the Southern Cross. So I am going to do another close-up so you can see the Southern Cross. So as you can see, the cross is tilted now. This is an easy constellation to find in the sky, only visible in this hemisphere, and a good guide to find the south celestial pole. This is a projection of the Earth's south pole. So during the night, the stars appear to revolve around this point. So to find this point, we will do this. We are going to um, extend in our imagination the longer stick, this one, the longer stick of the Southern Cross, right here, about 4.5 times. So we are going to extend this and project 1, 2, 3, 4.5, and more or less like here, we have the south celestial pole. So this sun also indicates the south cardinal point. So if you look at the horizon from this position, the horizon is the south cardinal point. Okay, so this is basically a nice example of orientation in the night sky. Okay, so this is the conclusion of our visit to Cerro Paranal. We are returning to the platform and we are going to return to the daytime view. Okay, so now from this moment we are going down to 2,400 meters in order to visit a very special oasis. For this purpose, we have to rotate the view and search for the base camp of Paranal. So now you can see the base camp in the distance. Okay, we are going to visit the base camp virtually, and from here, this is the base camp, we will visit the residence of Paranal. The residence is a place where the ESO staff can stay and rest. It's this one. Okay, so we are going to take a closer look. And the residence is the home of the ESO staff during their work in the desert. So let's enter now. Okay, so now we are in the residence. The residence is the place where the workers can enjoy a more humid air. They have a swimming pool, green areas, and also rest compared to the desert and the intense sunlight from the outside. So during this time at the residence, as you can see, this is a very nice place. During this time at the residence, I think we have some time to respond to the questions we have from the public. So, Hector, do we have more questions?
Yes, Farid, we have a couple of questions. Okay, so Juanjo Garrido asks us, how much has affected observation the increased usage of low Earth orbits, such as the new satellite constellations like Starlink and whatnot? Could you comment on that?
Yeah. Well, yeah, that's correct. This is a concerning issue among the astronomical community because the new satellite constellations in the future they are expecting to have thousands of satellites in the sky, and eventually, yeah, this could be a problem for astronomical observations. So far, it hasn't affected too much because you also need to consider that in a telescope you have a very small field of view, so you are actually looking in a very small portion of the sky. So it has to be a coincidence to have a satellite crossing the same field of view, but it could happen. But right now, I think we have time. We still have time to correct this problem, to try to adjust the satellite, I don't know, materials maybe to reduce the reflection of sunlight. So it could be better to avoid disturbances to astronomical observations. But right now, so far, it hasn't affected too much. But because we are still on time to try to do some corrections and work together with the I don't know the satellite manufacturers in order to prevent a bigger problem for astronomy.
Okay, thank you. And we have another question here from Andrei Popov. I hope I pronounced that correctly. Does the electrical conductivity of planetary nuclei affect the location of planets near the sun? Okay, that's an interesting question. And that requires to talk about planetary formation a bit. So planets, they form together with stars. And what happens is that a cloud of, molecular hydrogen collapses because of gravity. It gets fragmented. The different fragments will form different stars. So we focus on one of the fragments, and as it keeps collapsing, it will start to rotate to conserve angular momentum, and then it will form a protoplanetary disk with most of the mass concentrated at the center, and a disk where the planets will be forming. And when the star at the center starts producing nuclear reactions, it will produce radiation, stellar winds that will push some of the more lighter molecules of the cloud to the outside. And this is one of the reasons we will be finding in our solar system rocky planets in the inside and gas giants outside. Or at least that was what we used to believe until we actually start detecting exoplanets and we find giant gas planets very near their stars. So this was revised, and what we believe now is that the interactions, gravitational interaction between the different planets can cause them to migrate. And this is not something that is completely resolved right now. We still don't really know how we pass from a gas from the size of dust to go to rocks the size of hundreds of meters. Once we have rocks the size of hundreds of meters, it's just gravitational interactions that cause them to coalesce into a larger rocks or to crash into each other. Okay, so how do these will be affected by electrical conductivity? Well, we can imagine that what happens if we consider the role of magnetic fields in all this. So on the one hand, the magnetic field on a giant class of molecular hydrogen could act against gravity in the collapse. It could also change the way the different molecules coalesce together to form different planets. How do this is really something that we don't know right now. This is something that is currently being investigated, and I am really not an expert on planets, but I hope this gives you a bit of an idea of what is happening here. So the magnetic fields and the solar winds would affect the way the different molecules get together or not. And if we are at the beginning when we're just forming dust-sized particles, then the electromagnetic interactions between the particles will be more important than gravity to a degree. I hope that gives a bit of an idea. It's an interesting but complicated question.
Thank you, Hector.
And we have another one. Let's see. We are tied to the Earth's magnetic field, so we live here. If we live on another planet, then our age could reach 5,000. Uh, Not necessarily. Okay, so the role that the magnetic field of the Earth has on our life is that it shields us from the solar radiation. So basically, without magnetic field on the Earth, a lot of charged particles will be hitting us every time, and we will get cancer a lot faster than what we have right now. So we probably would live less longer.
Yeah, if I can add something, maybe you can do a trick to reach um, another age. For example, if you are in a planet with a very short orbit time, for example, in Mercury, it's just an example. The orbit of Mercury is 90, about 90 days. Okay, so if you can live in Mercury in the same amount of time we have on Earth, for example, someone of 30 years on Earth, on Mercury, it will have 4 times the age. It will be about 120 years, you know. So
Yeah, yeah.
basically, the age is also a concept based on the orbit of the planet around the sun. So this is just, of course, maybe it's not related to the question, but it's just to try to give you an insight about what this means the concept of age exactly, and it's related to the orbit of the planet around the star.
Mhm.
Okay,
Okay.
Hector, do we have more questions?
Uh, we have a couple more greetings from Ariane, and I don't see more questions. So let me ask you something. If any of our viewers just happens to be in Chile or planning to travel in Chile, could they visit the observatory in person?
Yes, yes. It is possible right now to visit Paranal. It is possible to visit La Silla. So in both cases, we have public visits available on Saturdays, 10 a.m. and 2 p.m. So in order to visit one of the observatories, you need to enter to the ESO website and you need to do a reservation, an online reservation. And so you need to choose what is your preference of date to visit the observatory. And of course, you need to do it with some days in advance because we have a lot of interest of people wanting to go there. So it's better to do it in advance in order to have an space uh, to find a spot to visit the observatories. So yeah, of course you can do it, and it's completely free, but you need to go with your own means of transportation.
Okay, thank you for it. Well, for my part, I say goodbye to our viewers. It was my pleasure be with you today, and I hope that you enjoyed the tour. And if you like it, please let your friends and family that might be interested in this type of tours. That we have tours every weekends. We are alternating between La Silla and Paranal, sometimes in Spanish, sometimes in English. So you need to be keep an eye with our social networks. And I say goodbye, and my pleasure to be here with you today.
Okay, thank you, Hector. Also, we remind you that the, the visit, see, that the information and pictures, all this information is available on the ESO website. Okay, so you can find more information there if you want to know more. Okay, also we have a survey to receive your comments about this tour. So the link to the survey will appear in the comment section of this streaming right now. Okay, so I hope you like this virtual experience. Please stay alert to the ISO social networks to know when we will have the new virtual tour in Spanish or English. So on behalf of ISO, I want to say thank you very much for your presence. Okay, so thank you and goodbye.